Lecture 8.4, a number of minimas, maximas, and the diffraction pattern. Up to this point, we have used the sine theta sequence from the path difference equation to determine the m value for interference. Because interference and diffraction are so closely related, what we found here is that the path difference equation for interference and diffraction are opposites of each other. Here's what I mean. So if I look at d sine theta, we can see here that I have MC lambda, and that gives us constructive. But if I look at diffraction, I have A sine theta, and this gives me destructive. And if you look at destructive for interference, we wrote MD plus 1/2 lambda for destructive. And on the other hand, this is an approximate value. It's not an exact value. This was NC plus 1/2 lambda, and that gave constructive. And that's what I mean by them being opposite. So all of these relationships are exact except this guy. This is approximate for the first three constructive interference cases in diffraction. The process for determining the minimas slash maximas for diffraction is exactly the same as for interference. And that means here is that if I look at minimas, then I look at the path difference equation. It reads A sine theta of n, then I'm going to get nd lambda, and I know that n is equal to plus or minus 1, plus or minus 2, all integers. Now, if I isolate the sine of theta, I'm then going to get plus or minus nd of A over lambda. In other words, the diffraction parameter. So then, when we start the sequence, then the sequence then goes something like this. I have plus or minus A over lambda, and then I start with 1. and then I keep doing this, then I have 2. And then we keep doing this until sine of theta of n is greater than 1, and therefore it stops the sequence. Now, there is a more efficient way to determine the value of n. And the way we do this here is that we start with the path difference equation, and calculate the maximal value of n. And so the way we do this here is that we set the sine of theta. We know that its max value has to be +1, and then we just substituted it. So if we do this, then I'm going to have a sine of theta max. So if that's maximal, then that means that n is maximal times lambda. So what you're seeing here is that then Nmax, which is a over lambda, is exactly the diffraction parameter. Now we got to be careful here. And the reason why we got to be careful is that this is not ND or NC. That's something that has to be figured out still. So what we're going to look at is that we're going to look at various values. So we will look at 3 possible values of Nmax and determine the number of mins and maxes, as well as the ending part of the diffraction pattern. And so these 3 cases are: 1, we're going to look at Nmax equal to an integer. And what we're going to find here is that if this is an integer, then at the end of the diffraction pattern, a minima occurs. However, if Nmax is an odd half integer, then at the end of the pattern, a maxima occurs. And then our third case here is that we're going to look at Nmax being a non-integer, and so what that tells us here is that at the end of the pattern, we have a partial maxima occurs. So we want to go through those cases here and really get a sense of when that actually happens. So here we go. I'm going to start with case 1. And in case 1, we're going to set Nmax is going to be an integer. So what we have to do here is that we have to handpick values of the wavelength and the slit opening or the aperture opening. Okay, so here's what I'm going to choose here. So I'm going to pick lambda equals to 600 nanometers. And then I'm going to pick A as 3,000 nanometers. So what one can look at now is that now I can calculate the diffraction parameter. Which is then going to be A over lambda. In this case, it's going to be 3,000 nanometers divided by 600. So you can see here is that this guy is 5. So the fact that this is 5 here, that means here that this is an integer, which means that we expect a minima at the end of the diffraction pattern. So now we're going to use both techniques to calculate the n value, and then I'm going to go to the more efficient way of calculating it. So the first thing that we're going to do is that we're going to look at the sine theta sequence process to calculating n. So note that this does not calculate n. We have to look at the series to find out who's the max. So here we go. So in this process, if I'm looking at the minimas, then that means I set up my sine of theta of n, and then this is then going to be plus or minus n over A over lambda, but in this case, we see that diffraction parameter is 5, so this is really plus or minus n divided by 5. So now we start our sequence. So if we start our sequence, we can see here that we're going to get plus or minus 5 times 1. And then you can see here is that I have to keep going until I exceed sine theta greater than 1. So if you start to move through the sequence, you could see here that this is going to be 2, 3, 4, and then we get to 5 and 6 here. So you could see here that I get to 5, and now I get to 6. And what you're seeing here is that this is the point where it exceeds sine theta equal to 1. So right away, we can pick off that the n value we see here is that nd is equal to 5. So then we know that the minimas are symmetric. So then this tells me here is that the number of minimas should be twice because they're going to be in the left to the right. So this will be 2 times 5. And this tells me that I have 10 minimas. So I know I have 10 minimas. So if that integer tells me that it's going to be a minima at the end of the diffraction pattern, that means that NC has to be smaller than ND. So now if I go to the maximas, I do the exact same thing. Now note that this is not an exact relationship, so we say it's an approximate. And we have that. Now, I said 1 here, but it really should be 0.5. So now I'm going to start the sequence again. So if I look at the sequence, now note that this is plus or minus, so I'm going to do the exact same thing as before. So then this will give me 1 plus 0.5. And then I'm just going to start adding the 0.5 instead of writing it out separately. So then this is going to be 2.5, 3.5, 4.5, 5.5. So if I start to look at this sequence here, you could see here that at this point, it exceeds sine of theta equal to 1. So that means here is that because I have 1, 2, 3, 4, that tells me immediately then that NC is equal to 4. As expected, it is smaller. So now I go and I start counting, and the way we count these is that there's a couple ways to do this. This would be 1 plus 2NC. The 1, of course, is for the central max. So then if I plug this in, I'm going to get 2 times 4. That gives me 9 maximas. So now we have our pattern. So what we can do here is that we can then draw out the pattern here. So drawing out the diffraction pattern, what do we have? I'm going to be looking at the intensity function. The relative intensity. So then I start to look at this, and I have to go where? I have to have 4 minimas. No, not 4. We have to have 5 minimas. So I got to go 1, 2, 3, 4, 5. That means here is that at this, so if I start labeling these, this is 1, 2, 3, 4, 5. And remember, this is the value of n. So the fact that I know the n, it immediately, I could have just calculated the minimas, and I would have known what the pattern was. And then you can see here is that these peaks here, they occur at roughly 1.5, 2.5, 3.5, and you could see that this will then be 4.5. So there you go. So that means here is that this location right here is at 90 degrees. So that's the way we did it for interference. But now I want to show you a slightly different way, which is it uses all the same things, but it's more powerful, as you'll see. So now we want to do the maximal value of the Nmax process. So let's follow that. So if I look at this process here, that means here is that we set sine of theta max equal to 1 in the path difference equation. So when we do that, we then have a sine of theta max. This is now going to give me the Nmax value times lambda, which then tells us that then we get the diffraction parameter immediately, which we already said was 5. But this 5 here tells me that it's Nmax. Okay, we now have Nmax. I said this already, but I want to remind you that this here, this is Nmax, not Nd or Nc. And as before, we said that because this is an integer, we know that the end has to be a maxima. So now start summing the n values for minimas and maximas until they exceed Nmax, which in this case is 5. So here we go. So then I'm going to go minimas. That implies that I have Nd. So then I start to look at the possible values. I'm going to have plus or minus 1, 2, 3, 4, 5, 6. So now if I come in and I start doing this whole process, just like we did before, you could see that when I get to 6, this exceeds Nmax equal to 5. So therefore, the sequence stops. So if the sequence stops here, then this immediately tells us that we have Nd equal to 5 and 2Nd, which is 2 times 5, then gives me 10 minimas. So instead of exceeding sine of theta, we're just exceeding the maximum value of Nmax. And then I could do the exact same thing with the maximas here. In this process, we know that Nc, they go through values that are half integers. Okay, multiples of half integers. So in this case, it's got to be plus or minus 1.5, 2.5, 3.5, 4.5, and then I get to 5.5. So now, if I start looking at these, you could see here is that when I get to 5.5, that has now exceeded 5. So in this case, it exceeds Nmax equal to 5. So the sequence stops. So now if I keep going along here, then I have Nc equals to 4. And then we have 1 plus 2Nc, which will be 1 plus 2 times 4, which gives us 9 maximas. So I get the exact same values as before, but this is way more efficient. So this is the way I'm going to do it here. So in comparing this process of Nmax to that of the sine theta sequence, this one is more efficient. And in the future, I will use it in all calculations. As soon as you see the process, you'll see that we won't even do the sequence. We're just going to look at the diffraction parameter and go from there. Now, what I want to do here is that let's say let's use an applet to help visualize the pattern. Now, I can't show you the intensity profile because they're too small. But I'm going to use the applet by Vent single slit diffraction. Oops. Applet. And as we've been doing all semester, you would go to the lecture page and find this applet. So let's go share that. So here's the applet. So what I have to do here is that when you're looking at it, we are looking at two values where we set the wavelength to 600, and then we set the slip width to 3000. So let me go set this to 3000. And then if I hit return, the pattern has now changed. Now what I'm going to do here is that I would love to use the intensity profile, but you could see that this doesn't really help. And this diffraction parameter or diffraction pattern helps a little bit more. And you could see here that I have my central. Then if I start to count, look what I get. I get 1, 2, 3, 4 minimas. But if I go to 90, you could see that it's 0 right there. So this is what I'm going to take into my my OneNote and show you what do I have here. Okay, so I'm going to go back and I'm going to share my screen right here. And let me bring this down a little bit. And here's the applet that I have here. So what you're seeing is this guy. In fact, I'm going to move it over here. So now if I start looking at the minimas, that's really the one I'm going to look at. You could see that there's a minima here, here, here. And this is at 90 degrees here. And it's 0 right there. And then I start going all the way around. And then there's another one right there. So if I label these, this is then -1, -2, 3, 4, 5. And this is +1, +2, +3, +4, +5. So once again, we're saying that there's a minima at 90 degrees there. In this case, it's -90 degrees. So what I'm going to start to do here is that I'm going to start to move away from even looking at the sequence and just look at the pattern to show you that we can go immediately to what the diffraction pattern is just by looking at the fraction parameter. So once again, any Nmax value that is an integer will always have a minima at the endpoint, in other words, at 90 degrees of the pattern. So here are some more examples. So we picked 5, but check this out. So what happens if I have a pattern that looks something like this? And I get Nmax equal to 1. That tells me immediately that my pattern looks like this. And so that means here is that at this point, this is 90 degrees. And you could see here that this is n equal to 1. So if that's the case here, then if I look at them, that tells me here that if I look at the number, if I look at the value for, how do I want to do this here? If I look at my values for my maximas, nope, excuse me, my minimas, we can see here that that's an integer, so that immediately tells me that nd is equal to 1. And if nd is equal to 1, then what it tells me here is that then 2 times nd gives me that I have 2 times 1, which gives me 2 minimas. You know, I'm going to run out of space, so I'm actually going to bring this down and do that. So right away, I have this pattern right here. And just by looking at this pattern, we immediately see here, so when I go to the maximas, NC, its first value, so when you look at NC, its first value is 1.5. So this immediately tells me that this has already exceeded Nmax equal to 1. So this implies here is that so then this immediately tells me that NC is equal to 0. Therefore, 1 plus 2 times 0 gives me 1 maxima. So note, I did not do a sequence. I can continue on. So let's say I have a pattern that looks something like this now. And what I'll choose here is that in this situation, I could pick Nmax equal to 2. So I know that because that's an integer, it's going to end there. So now if I go and I plot this guy, it's right here. I see that this is 1. I see that this is 2 here. So when I look at my pattern, now I could talk about the minimas and maximas. So in this situation, we see here is that the minimas has to then have ND equals to 2, which then tells me that I'm going to have 2ND, which then will be 2 times 2. So I'm going to have 4 minimas. Because that's what Nmax is telling me. So now if I go look at the maximas, that tells me I'm going to look at NC. So if I look at NC, I have to look at the values that are less than 2. And we can see here is that the only valuable possible is 1.5, because right here we have now exceeded Nmax of 2. So then this tells me here that this guy is my NC value, which then says that then I have 1 plus 2 NC. So this gives me 1 plus 2 times 1. So I'm going to have 3 maxes. And I can just keep going on. So instead of looking at these details, let's see if we can just do it by inspection. What happens if I have a pattern that's now Nmax equal to 3? So then we just start the same process here. So then it's going to go 1, 2, 3. And even though I didn't say this last time, this was at 90 degrees. This is at 90 degrees. So in other words, we know that this point is 1, 2, 3. So right away, if I look at the minimas, not the maximas, the minimas, we immediately see that ND has to be 2, and therefore it has to have, nope, this is 3, not 2. So then it has to have 2 times 3, so I'm going to have 6 minimas. And if I look at my maximas, it can't exceed 3, so the only way we can conclude here is that that has to be 2.5. So it's got to be 2. So therefore, this tells me that this is 1 plus 2 times 2, which then gives me 5 maxes. So just by playing this game, we can immediately infer what the pattern is. With a little bit of practice here. So now let's go to the next case. The next case that we want to look at is case 2. In case 2, we want to look at odd half integers. Oops. Of Nmax. So I will only use the more efficient process for calculating Nmax, and then from here, that tells us then what is ND and what is NC. So let's try a different situation because we want odd half integers. So then I'm going to select lambda equal to 600 nanometers, and then A is going to be 1500 nanometers. So here we go. So from the path difference equation, we see here that we get A sine of theta max is then going to give me Nmax times lambda, which then tells us then that Nmax, in this case, is going to be A over lambda, which is 1500 nanometers divided by 600 nanometers, which then gives me 2.5 for Nmax. So in this situation, we could see here is that the fact that this is a half integer, this means that this is close to a maxima at the end. And remember, we say close here because they're off by a little bit. So now, let's start summing the values. So if I sum the values here, now I'm gonna, so now, let's start summing the n values. So then if I have ND, so if I look at the minimas, that tells me that I have ND, and then I go plus or minus 1, plus or minus 2. So I go 1, 2, and remember, I have to go to the point till I exceed 2.5. 3 exceeds it, so now we exceed Nmax equal to 2.5. So the sequence stops. So therefore, this tells me here is that ND is equal to 2, and 2ND is then going to be 2 times 2, which will give me 4 minimas. So I know my minimas. Now let's go for the maximas here. So if I look at the maximas, then I have NC, and remember this is approximate, so then this will be plus or minus 1.5, then I get 2.5, and then I get 3.5. And so as I start to sum these, you could see that the sequence ends at 3.5 because I exceeded, again, you exceed Nmax of 2.5. So that means I only have 2 values for NC. So then this means here that NC is now equal to 2. And if it's equal to 2, then my pattern is then going to be 2, it's going to be 1 plus 2NC, which will be 1 plus 2 times 2, which then gives me 5 maximas. So now I know everything about the pattern. Let's draw out the pattern. So again, we know that there has to be 4 minimas, and the last one has to be close to a maximum. So then I'm going to go So I got to go 1 minima, 2 minimas, and then I stop right there. So what you're seeing here is that this is close to 2.5. So if I start labeling these guys, it looks like this. So then I see that this guy is 1, this guy is 2. And by the way, if I was to keep following this, you could see that this point is 3, but that doesn't make any sense. So then what this tells me here is that this guy right here is 1.5, approximately. This guy right here is approximately 2.5. So there's my pattern. Now, what I want to do here is that I'm going to go and I'm going to copy the fent applet wording and use that again. So what we want to look at is that I'm going to come in and I want to use this guy again. So let's go put in and get 2.5. So our values were 600 and 1500. Let's go look at the applet again. So sharing my screen. What you're seeing here is that now this is at 3000. So I got to put in 1500. And what you're seeing here is that, note that there's the central max. Now let's count the minimas. There's 1, there's 2, but note that there's light here at 90 degrees. So if I copy this and I go and I put this into my OneNote, it looks something like this here. So if I go and I look at my values, I'm seeing here that I have a minima here, but note that at 90 degrees right here, there's light there. So this is a maxima at 90 degrees. And then if I go look at the other ones, there's another one right here. You could see here that this is now going to be, -1, -2. This will be +1, and this will be +2. And then I could come in and I could add the other ones here. This is -1.5 approximately. This is -2.5. This is +1.5. And then this will be 2.5 with the plus. So what I'd like to do here is that just to get a little bit more practice here, let's look at this. So any Nmax value that is an odd half integer will always be close to a maxima at the endpoint. And again, that's 90 degrees of the pattern. Here are some more examples, just like we did with the integer here. So in this situation, let's not think about the sequence so much. So let's say that we have this guy now. And what we're going to pick here is we're going to pick NC equal to 1.5. So then if I look at my pattern, that means this guy has to end at the value of 1.5. So that means here, so when I'm looking at this, this is where it ends. And then here, this is my 90-degree point right here. So if I was to keep following this thing, I would get to 2. So now you could see here is that this is 1, this is 2 here, but the pattern never gets all the way down to there. So if I look at this thing here, we're saying that this value right here, this is approximately 1.5 right there. So now we can go fairly quickly on how that works. So I'd probably look at the maximas first, and we can clearly see that NC is equal to 1. And therefore, if I look at the number of maximas, it's going to be 1 plus 2 NC, which will then give me 1 plus 2, which gives me 3 maximas. If I look at the minimas, you could see that I have a 1 minima on the right, and I have to have another one on the left. So therefore, ND is equal to 1. And so then that tells me that 2ND is then going to be 2 times 1. I'm going to get 2 minimas. What happens if I have something that reads, let's just do one more here. What happens if I have a value that looks something like this? Let's say that this is NC equals to, how about 5.5? So if I look at this pattern here, it's got to go 1, 2, 3, 4, 5. Let's count here. I think I made a mistake here. So this will be 1, 2, 3, 4. That's 5. So now look what happens here. So now I'm going to have a little tiny one. And then this guy right here is 6. So that means here is that at this point right here, this is at 90 degrees. And so now if I go and I look at my max values, remember, these are all approximate. This is approximately 1.5, 2.5, 3.5, 4.5, and right here, this is 5.5. So just by inspection, we could start to look at how many maxes and mins are there. So if I look at the maxes, we see here is that there's 5 values. So therefore, NC has to be 5. And if NC is 5, that tells me then I'm going to go 1 plus 2 NC. And this will be 2 times 5 is 10. So this gives me 11 maxes. And I could say the same for the minimas. I'm going to get, if I go to, if I can't exceed 5.5, so the smallest integer here, by the way, I was putting NC up here. It should have been Nmax, not NC, Nmax. So then here we could see that it goes up to 5. So then ND must be 5. But then this is 2ND, so that has to be 10 minimas. You could see why this is more efficient. So then the last case that we want to look at is that we want to look at the non-integer values. So this is case 3 now. We're going to look at non-integer Nmax values. So let's look at a couple values of Nmax being a non-integer. So the first case that I'm going to look at is that I'm going to choose lambda equal to 600 nanometers, and I'm going to choose A equal to 1600 nanometers. So again, I am defining these to force the situation to give me exactly what I want. So what this tells me here is that from our process before, we know that Nmax is the diffraction parameter, which is now 1600 divided by 600, and this guy is now 2.67 for Nmax. What does this mean? So we're seeing that this is not an integer. This is not a half integer. So that means that the end of the diffraction pattern must be a partial max. Since Nmax is not an integer or a odd half integer, the end of the diffraction pattern is a partial maxima. So let's look at the pattern. So the pattern is as follows. So let me bring this up a little bit. So here's my pattern. So I know that this is 2.67. So then I'm going to look at my pattern here. So it's got to go, so now look at it, it's got to have one minima. It goes to two minima. And then, so if I start to look at this thing, 2.67 is closer to 2.5 than it is to 3 here. So then I know that this guy goes to 2.5, but then it stops after it peaks. So when I'm looking at this point here, this value right here is at 90 degrees. So let's go back and look at the details here. So if I look at my numbers, this guy is 1, 2, and 3. So it never gets to 3. But if I now look at my values, this is 1.5 approximately. This guy is 2.5. So this point right here, this point right here, this is 2.67. So what this tells me here is that this value tells me that it's closer to the secondary maxima than it is to the third minima. So that's telling me the location. So what you're seeing here, so if you look at just the peak, so looking around the peak, here's what we see here. So when you're looking at the peak, it looks something like this. So again, so if you look at this point right here, this guy right here, that's 2.5. So what you're seeing here is that if this is 2.67, it tells me that I've gone down, right? I've gone down by how much? By 0.17, means it's just past the secondary maxima. That's what that 0.17 value means. Let's look at a second case here. Here, we want to choose lambda equals to 600 nanometers, and we're going to pick A equals to 2500 nanometers. So of course, I'm picking these randomly. So now you could see here that this is Nmax, and Nmax is then going to be 2500 over 600, which then gives me a value of 4.17 for Nmax. So once again, right? Once again, this is not an integer or odd half integer. So the end of the pattern is a partial maxima. So let's draw this pattern out. So we know that because it's 4.17, we have to go past 4 minimas. So let's do that. So we're going to go 1, 2, 3, 4, and then it just goes up a tiny bit. And then I have just a little tiny portion, which is right here. This is at 90 degrees. So if I start to look at my values, you could see here that this is 1, 2, 3, 4. And if I kept following the pattern, I'm exaggerating the pattern right here. It's not that wide, but that would be 5. So now let's go look at my values of the half values. And then right here, this is 4.5. So you could see that it doesn't reach it here. So very similar to up here, what did we do here? We looked at our peak value, right? This value right here, this one is 4.17. And so when we do that, we really are saying here that this tells me that this is closer to the fourth minima than the fourth secondary maxima. Again, that's telling us our location. So now, again, if we look at what's actually happening, our peak sort of looks like this here. So if I look at this thing, it goes like this, and then this guy goes right here. So what I'm saying is that looking at my picture here, this guy right here, I think I'm going to keep going up like this here. And you could see that at this point, this guy is at 90 degrees. So, oops. And there's only this little tiny bit here. So we can see here is that this guy is at 3.5. This one's at 4.5. And then our minima right here is the fourth. So then that tells me that when I look at this little tiny peak here, that little tiny dot right there, what this tells us right here is it says that this is 0.17, right? That 1.7 means it's just past the fourth minima.